Hi everyone, welcome to this video lecture on Paper 3, Unit 1, Aberrations. In this video lecture, I would like to explain the monochromatic aberrations, coma and astigmatism. The first topic is coma. Coma may be defined as when a point object is situated slightly off the axis, the image of the point object found by the lens is found to have an egg-like or comet-like shape. Hence, the defect is called coma. That means the image of a point object placed far off the axis of a lens is not a point image, but appears as egg-like or comet-like shape. So, this defect is called coma. This can be explained as, consider an off-axial point in the object OA. Let the lens be divided into different zones such as 1, 1, 2, 2, 3, 3 and so on. In the diagram, OA is monochromatic object, that means it emits monochromate light. A is the off-axial point. This is a large aperture convex lens. This lens may be divided into different zones 1, 1, 2, 2, 3, 3, 4, 4, etc. as shown in the figure. The rays leaving the point A and passing through the zones 1, 1, 2, 2, 3, 3, etc. of the lens are brought to focus at different points I1, I2, I3 and so on. So, the image is not in a perfect focus. This defect is known as coma. It arises due to the following reasons. Different zones of the lens produce different lateral magnifications, and each zone forms the image of a point in the form of a circle. Coma aberration is similar to spherical aberration, but in the spherical aberration, the point object placed on the axis, but in coma, the point object is far away from the axis. The spherical aberration is due to fact that different zones of the lens have different focal lengths, but coma is due to different zones of the lens have different lateral magnifications. The radius of the chromatic circle increases as the radius of the zone of the lens increases. At I1, the chromatic circle is a point. Above I1, circles of increasing radii are obtained. The shape of these circles are shown in the figure. The resultant image is comet-like. Hence, the aberration is called coma. Coma may be eliminated by using stops, by using cross lens, by using epileptic lens, etc. The first method is, coma may be reduced to certain extent by the use of proper stop placed at a suitable distance from the lens. This restricts the outer zone and allows only the central zones to refract the rays. Coma may be minimized by designing lenses of suitable shapes and materials. A cross lens with mu is equal to 1.5 and R1 by R2 is equal to -1 by 6 forms an image of an object at final distance sufficiently free from coma. And also, by using the cross lens, we can minimize the spherical aberration. A pair showed that the lenses are completely free from spherical aberration and coma if the following sign condition is satisfied. Mu1 y1 sin theta 1 is equal to mu2 y2 sin theta 2. Here, theta 1 theta 2 are the angles which the conjugate rays make with the axis. Mu1 and mu2 are the refractive indices of the object and image spaces, and y1 and y2 are the heights of the object and image for the zone. When the medium on both sides of the lens is the same, then the above condition reduces to y2 by y1 is equal to sin theta 1 by sin theta 2. Here y2 by y1 represents lateral magnification. If the lateral magnification is the same for all the rays of light, irrespective of the angles theta 1 theta 2, then the coma may be eliminated. A lens satisfying the condition sin theta 1 by sin theta 2 is equal to constant is called an apneutic lens. So, by using apneutic lens, we can minimize the aberration coma. The condition sin theta 1 by sin theta 2 is equal to constant is called a base sign condition. In this way, we can minimize the aberration coma. If these conditions are followed, both coma and spherical aberration may be minimized. Now, the next aberration is astigmatism. When a point object is situated far off the axis of a lens, the image formed by the lens is not a perfect focus. The image consists of two mutually perpendicular lines separated by a finite distance. Moreover, the lines lie in perpendicular planes. This defect of image is called astigmatism. Astigmatism can be explained by using the diagram shown in figure. In the diagram, O is a point object placed far away from the axis of a convex lens of large thickness. In the lens, we can assume two mutually perpendicular planes M1 and M2 and S1 and S2. The plane M1 and M2 is called meridian plane, which contains object point O and principal axis of the lens. S1 and S2 is a plane perpendicular to plane M1 and M2 called sagittal plane. The light rays from the object O, after passing through the meridian plane M1 and M2, meet at point M. The image at point M is called meridian image, and the light rays passing through sagittal plane S1 S2 after refraction meet at point S, and the image at point S is called sagittal image. The two images lie on two mutually perpendicular lines, and the lines are in the two mutually perpendicular planes. If a screen is moved between M and S, an irregular patch of light is obtained. Thus, the image never approaches to a point image. This defect is called astigmatism. When the screen is moved between S and M, the patch of light reduces to a circle. This is known as circle of least confusion. This is the nearest approach to a point image. The distance between the lines M and S is a measure of astigmatism and is called the astigmatic difference. The astigmatic difference is positive in case of convex lens and is negative in case of concave lens. The astigmatism can be minimized by using the following methods. The astigmatism can be eliminated with the help of straps by placing it in a suitable position. In case of concave lens, the astigmatic difference is negative, while in case of convex lens it is negative. Therefore, a suitable combination of convex and concave lenses separated at a suitable distance may be used to reduce the astigmatism. For a system of several lenses, the astigmatism may be eliminated by adjusting their positions. Such systems are widely used as photographic objectives. In this way, we can explain the aberrations, coma, and astigmatism. I will explain the remaining defects, curvature of field, and distortion in the next video lecture. Thank you.